Hi, and welcome to our video. This little guy is acyclovir. He's a common antiviral primarily used in the treatment of herpes infections, shingles and chickenpox. What we hope to do with this video is give you a good overview of the drug itself, right from when it was first discovered in the lab, through its synthesis method, all the way to its mechanism of action when it enters the body. Along the way, we'll touch upon some things that will be useful in pharmacy practice. So let's start by looking at the actual structure of acyclovir. One thing to note about the structure you're about to see is that it's the drug in its prodrug form. It doesn't actually exist in this structure once it's active in the body, but we'll talk about that later on in the video. As you can see, acyclovir is a relatively small molecule, but despite its small size, it still has a number of functional groups. Let's take a quick look at some of these now. Within the ring system, we can see a primary amine, an amide, and an imidazole ring. The bulk of acyclovir's structure is made up of this bicyclic ring system, which helps increase the drug's lipophilicity, alongside this alkane chain that contains an ether. At the end of this chain is a primary alcohol. Take note of this alcohol because it's this that plays the main role in the drug's mode of action. So just by looking at acyclovir's structure, we can tell a great deal about how it will behave as a drug by seeing if it fits Lipinski's rules. Acyclovir has 3 hydrogen bond donors and 7 hydrogen bond acceptors, and a log P of -1.56. This combined with a molecular weight of less than 500 means that it does fit Lipinski's rules, making it an ideal candidate for oral formulations, which are given in varying strengths from 200mg to 800mg. Feel free to pause the video at this point to have a look at the other features, including its polar surface area, that all help make it a good drug to take orally. So let's go back to the start of acyclovir's journey, which all began at the Wellcome Lab in Kent in the 1940s, with 2 researchers, George Hitchings and Gertrude Elion. They were looking at sulfur drugs, which made Hitching consider if other substances that interrupted microbe metabolism could be used as drugs. Hitching then started looking at nucleic acids and tasked Elion, his research assistant, with looking at purines specifically. They learnt the importance of purines and how bacterial cells were unable to produce nucleic acids unless certain purines were present. By the 1950s, they produced 2 compounds which were effective at blocking the virus. This was the first instance of rational drug design, and they are hailed as the founders of this field. In 1967, Hitchling retired and Elion took over as head of the research group. Research then shifted to antiviral medication after they learnt they had a similar structure to a purine that could combat DNA viruses. In 1974, Dr. Howard Schaefer, along with his colleagues, synthesised a new compound, acyclovir, the first antiviral drug. Elion then began researching the effects of acyclovir, how it worked, why it worked, and its toxicity, and it showed a good level of potency, blocking the HSV1 and HSV2 herpes viruses. What was interesting was that the drug was inert until it met the virus. At this point, the drug was kept secret by over 70 researchers. By 1977, after 3 years of secrecy, the drug was finally announced in newspapers. And in 1979, the US patent for acyclovir was drawn, listing Schaefer as the inventor. In 1982, clinical trials started, and after FDA approval, the topical form of acyclovir became available to the public. By 1985, all forms of the drug became available. This included tablets, IV infusions, creams, and eye ointments. And in 1988, Elion and Hitchings received a Nobel Prize for their work with rational drug design. In the same year, the patent ended, so generic packs of acyclovir were then available. So that brings us to the end of acyclovir's timeline, which ends in 2016, when the drug was put onto the World Health Organization's list of essential medicines, which means it was deemed the safest and most cost-effective medicine of its kind. So now we know the structure of acyclovir, let's go down to the factory to see how it's synthesised. So now we've seen where acyclovir came from, let's follow him on to the next stage of his journey to see how he's synthesised. Acyclovir synthesis begins with benzoyl chloride and ethylene glycol in the presence of triethylamine to produce 2-benzoyl oxyethanol, which is an ester with a hydroxyl group at the end of the chain. 2-benzoyl oxyethanol in the presence of methanol and hydrochloric acid then produces 1-benzyloxyl 2-chloromethyloxyethane, which is a molecule that binds with guanine in the presence of hexamethyldiacylazine, then iodine and triethylamine, which produces 9,2-benzoxyloxyethylmethylguanine, which is a bonded version of the two, which then reacts with ammonia and ethanol, which removes the aromatic ring and oxidizes an OH. So that was how acyclovir was originally synthesised, but in the modern day, it's actually a much simpler process and has 2 steps. First, guanine is acetylated using acetic anhydride, acetic acid and phosphoric acid, producing diacetylguanine. In the second step, diacetylguanine is alkylated at the N9 position using various reagents, including acetic anhydride and phosphoric acid. The acetyl groups are then removed as desired, giving acyclovir. This synthesis is commercially favoured due to its high yield. One of the most important considerations is the production of the intermediate diacetylguanine. The yield can vary greatly depending on the choice of protecting group, which is essential to prevent alkylation later on in the process. There are several deviations from acyclovir. The main ones are pencyclovir, which is a topical formulation, gancyclovir, and valacyclovir, which are oral formulations. Viruses that acyclovir is used to treat are the varicella zoster virus that causes chickenpox and the herpes zoster virus that causes shingles. It's used to treat the HSV1 herpes virus that's spread through mouth-to-mouth contact and is characterised by causing cold sores. This is what acyclovir is most commonly used to treat with topical preparations. You'll probably recognise it under the name Zovirax. HSV1 does cause genital herpes sometimes too, but the HSV2 herpes virus has been found more likely to cause that, so acyclovir can also be used to treat genital herpes with HSV2 infections. So we know from earlier that Elion discovered that acyclovir isn't active until it reaches a viral cell. What this means is we know that the structure of acyclovir must change somehow to have an effect. What was discovered is that transformation is a triple phosphorylation which forms acyclovir triphosphate, the true active form of the drug. This phosphorylation is catalysed by thymidine kinase enzymes within the viruses themselves. These enzymes are also found in human cells, however the viruses are much more effective at phosphorylating the molecule. This is because the viral kinases have a much better structural activity relationship with acyclovir compared to our kinases. Because of this, there is selective uptake into virally infected cells, which is what makes acyclovir such a good antiviral. How it works is by preventing viral DNA replication, and it does this in 2 ways. The first is due to its similar structure to deoxyguanosine triphosphate, a building block of DNA. The drug can bind to the DNA polymerase as a competitive inhibitor, which prevents it being used to form any new DNA. The second way it stops viral DNA replication is through chain termination. Essentially what this means is that DNA polymerase catalyses the attachment of a molecule of acyclovir to a new DNA strand, but acyclovir isn't like normal nucleotides as its sugar unit is missing a hydroxyl group from the 3' position. This means the DNA chain can't be extended any further. So while replication of the viruses are clearly prevented with acyclovir treatments, we can also see that it doesn't actually kill the viruses, only that it stops them spreading to other new, healthy cells. This is particularly important in immunosuppressed patients. However, what this does mean is that small numbers of the virus can continue to live in the body, which is what causes individuals, such as those infected with the HSV1 herpes virus, to have frequent outbreaks of symptoms, such as cold sores. So how acyclovir actually works is by letting the body's own immune system build up enough to fight off the virus while stopping it from infecting new cells. So now, all that's left for you to know is how acyclovir works in the body. So let's have a look. So while we now know that acyclovir isn't active till it meets those infected cells, that doesn't mean that it's not without its side effects. It just means that it's difficult to figure out why those side effects are happening. Common side effects for all the different preparations of acyclovir include fatigue, headaches, vomiting, nausea, diarrhoea, abdominal pain. Important thing to remember about acyclovir, particularly in its use in renally impaired patients, is that it can cause nephrotoxicity in very, very rare cases, which is when the drug crystallises in the renal tubules, causing pain and a drop in renal function. This is serious as it can lead to renal failure, but we need to reiterate that it is extremely rare, so not something to really be worried about, just to be aware of. So on that serious note, that brings us to the end of our video. I hope that you've enjoyed it and learnt something new, but just to reiterate the key things to remember about acyclovir, and that's that it's a very safe and effective antiviral used for a number of conditions including chickenpox, and that it works from preventing the viral DNA from replicating. Thank you for listening. Bye!